Hello, good evening, and welcome to Lecture 2 of CENG 4412 Steel and Concrete Design. So, this is a recorded lecture. Normally I would record this in an in-class environment, but we did lose a little time due to Hurricane Harvey, so I'm doing a bit of catch-up recording to get us back up to speed. Okay, for this lecture I have a few objectives, or this portion of the second lecture I have a few objectives. First, I wish to identify types of steel structures. Second, I wish to describe types of loads resisted by these structures. Third, I wish to describe and discuss the difference between braces and moment frames. And fourth, describe diaphragm action and how we can use concepts to determine loads on building frames. So again, describe diaphragm action and use various concepts to describe and determine loads on building frames. Okay, so first of all, I just want to get one final mechanical property of steel out of the way. And that is the temperature effect of steel, or the effect of temperature on steel structures, or steel in general. Okay, so let's look at temperature, and this will be important if you consider things like forming, welding, forging, casting, any of these, any process for working with steel. But in terms of structural steel, this is most important for things like welding. Let's look at temperature effects. How does temperature affect the behavior of steel? Temperature effects. Well, just generally, if I were to create a plot, and this is going to be a very generic plot, and on this plot, on the vertical axis, I could put any number of things. I could put either E, the modulus of elasticity, or I could put Fu, the ultimate stress, or even, I should probably say Fy first, the yield stress, or I could put Fu, the ultimate stress. And on the x-axis, I might put temperature. Then, if I were to plot this, again, just a very generic curve, I would end up with something kind of like this. Constant initially, but then after a certain point, rapidly declining as we approach the melting point. But however, we do notice that well before the melting point, we actually reach a point of greatly decreased strength and stiffness. So we lose strength in terms of yield strength and ultimate strength, but we also lose stiffness. And so at where these points would be at, or to give you some general idea of the coordinates of this, the 50% point, about the 50% point approximately for each of these, where you're at about 50% of your room temperature, yield strength, modulus of elasticity, etc., would be about say 1,000 degrees Fahrenheit. And this is ultimately what allows us to hot roll steel shapes. We don't actually have to heat these things up to the point of being molten to form them. We can heat them up to, say, 1,000 degrees Fahrenheit. They're still solid, but they're very pliable solid. If you heat them up enough, they become like clay. Although you don't really heat them up to the point of being clay, because that would be like, more in this region. But if you take away 50% of their stiffness and strength, then they become much easier to form. And their actual melting point, or the point of zero strength, might be around 2,000 Fahrenheit or so. Okay, that's just a little side note that I wanted to cover. Now, let's look at some types of steel structures. That was just a sort of little bit of note from the previous lecture. Finishing up. Types of steel structures. Types of steel structures. Well, we can have a few. So you might have something like wall bearing, something that has heavy walls, maybe heavy walls of steel, concrete or masonry, that kind of thing, with that then has steel beams or girders, etc. Or you could have some sort of long span steel structure like a bridge, or you could have a steel skeleton. And in this course, we're really going to focus on the skeleton. This is the skeleton type structures. So buildings, common buildings, steel frame buildings, that kind of thing. Now, long span would be something more like a bridge design course. If you have, or I should say wall bearing, not just wall bearing. But yes, in this course, we're going to focus mainly on skeleton structures. And wall bearing, you could look a lot of that sometimes in concrete design courses. Well, this, of course, is a concrete design course as well. But wall bearing, that's almost like in the realm of masonry. But if we look at these various types, these then are used. All these various types of structures are then used in the various branches of civil engineering, including things like structures, transportation, transpo, geotech. So things like retaining walls, transpo being bridges, hydro, things like dams, and environmental. Things like water treatment plants, all of these things. Anyway, but let's look at this course. So let's think about this course. Again, this course we're going to mainly focus on the skeleton, at least in steel design. So let's look at the skeleton, and what kind of things are we going to be looking at? So for in this course, we're looking at the skeleton in terms of steel structures. For this course, we're going to be looking at skeletons, buildings that have well-defined steel skeletons. And in terms of subjects underneath this, what kind of members are we looking at? Well, we're looking at beams, columns, beam columns, and tension members. Now let's do the same thing, the same kind of breakdown for concrete structures. So again, here all I'm doing is just giving an overview of what kind of things we'll learn how to design in this course. Types of concrete structures, well, we'll have a few. We're going to have these three here, not tension members, because we really, of course, can't have concrete tension members. That doesn't really make much sense. But you'll have beams, columns, beam columns, plus, so these plus, plates and shells, so things like slabs, basically plus plates and shells. Mainly we'll be looking at things like slabs, floor slabs, foundation slabs, that kind of thing. And again, these also feed into the various applications of civil engineering, including structures, transpo, geotech, environmental. So even though I do consider this a structural engineering course, the things that we learn how to design in this course can be used in a variety of different applications. So for example, if you're skilled with designing concrete structures, you can use those. You can use that knowledge in designing a dam. If you're more into environmental, that knowledge can be used when designing the tanks in a water treatment plant, or if you've ever been to a water treatment plant, they inevitably have some large steel scaffolding or gantries and walkways over your various water treatment ponds and things. So anyway, this kind of structural design, this kind of concrete and steel design is reflected in basically all levels or all areas or specialties of civil engineering. Okay, so let's start looking at the loads that occur on a skeleton system. So we said we're going to focus mainly on the skeletons of buildings, and let's see what kind of loads are applied to steel and concrete skeletons. Loads on a skeleton system. If I can manage to spell skeleton. Loads on a skeleton system. Okay, well, we have a few. And the two main things that we're going to be looking at are gravity loads and lateral loads. Or we might say vertical loads and lateral loads. So let's break this down first before we start looking at what they're resisted by. So let's look at vertical loads and lateral loads. So what type of loads for each of these do we have? Well, vertical loads can be many different things. The big one, of course, is the self-weight of the structure. Ultimately, a structure, before it's good for anything, must be able to carry its own weight. But with steel and concrete structures, that's generally not that difficult, but depending on the structure. So self-weight, obviously. Any of your vertical live loads, so mainly your live loads. When we say a live load, we're talking about anything that can move within a structure. Furniture, people, sometimes walls if they can move through the structure's life. Dead loads that do not include the structure's own self-weight. So things like permanent installations that maybe aren't permanent pieces of equipment, permanent pieces of machinery, permanent walls that aren't part of the load-bearing system. All of those are dead loads. Then you also have things like snow load, wind load, well, at least wind, roof uplift, etc. Roof wind loads. Rain load, etc. Now, here in Houston, you're not going to see much snow load, but you're definitely going to see some rain loads, especially if you have a flat roof. Now, if you have if your building or structure has a sloped roof or a slanted roof, you're not going to have very much vertical load from your from rainforest. But if you have any kind of flat roof building, especially if you get any kind of ponding, then you can definitely have substantial vertical loads from rain loads. Lateral loads. Okay, now. This is actually the one that really tends to control in many cases, because intrinsically lateral loads tend to be harder to resist than vertical loads in most cases. But anyway, let's consider this. What are some examples of lateral loads? Well, the big one would be wind, and we just got out of the Hurricane Harvey, so we know all about lateral wind loads. What else? We have things like seismic. Sometimes live loads. Usually live loads are thought of as vertical, but sometimes live loads. Wind, seismic, those are your two big ones though. Well, wind and seismic, but there may be some other examples as well. Anything that is, so again, as a review, vertical of course is going to be any load that's up and down, and lateral load would be any load that acts side to side. And these fundamentally have to be resisted by two different functions, or two different mechanisms. So how are these resisted? So we have these types of loads. How are they resisted? Resisted by, well, the vertical loads are resisted by a very clear, just sort of direct load gathering process. So the first loads are gathered by say roof loads are gathered by the roof system. And any vertical loads in the interior of the building are gathered by the floor system. So we take the loads from there, then they're passed to the columns. Erase that line and show it going to the columns, and then the vertical loads are passed directly to the foundation. So fairly straightforward. Now, to actually design things to do that, is quite an art, and more, well, not really an art, more of a science, of course, an engineering science. Engineering is an art or a science, maybe a little bit of both. But anyway, so it's not necessarily easy to design your columns and your floor and roof system to do that, but it's a fairly direct process. You just have a certain tributary areas, you gather up your loads. You know where they're coming from, you know how large they are, you gather them up, and it's fairly straightforward, relatively, at least in comparison to lateral loads, I believe. So what about the lateral loads? What are they resisted by? Well, this isn't really done through either a direct transfer process like this. It's more like you have a series of ways of or a series of systems for gathering the load up, and we have a few of these. We have a few that we're going to discuss. First, we have braced frames, and these don't feed into each other. These are just systems that are available for dealing with lateral load. We have braced frames, unbraced frames, and diaphragm action. And today we'll discuss each of these in turn. All right, so let's see. Although I think I'm going to pause there really quickly, and then come back. All right, here we are again. Let's get started and pick up right where we left off. So now we're going to talk about braced frames, and let's start discussing how braced frames operate, what distinguishes a braced frame from an unbraced frame, and look at how each is capable of resisting a lateral loading, an applied lateral loading. Okay, so I'm going to look at braced versus unbraced framing. And for each of these, I'm going to draw a frame in elevation view. So braced frame, elevation view, and let's compare it to an unbraced frame. And an unbraced frame, elevation view. Let's do this more like this. Okay, so let's look at the differences. Well, first of all, draw the same frame in both. And just a very simple, maybe two-story frame with a couple of, maybe 3 columns. Something like this. And maybe we have 2 lateral loads applied. Actually, let me draw the other one first down here. So these would be pin connections at the bottom, perhaps. And pin connections down here as well. Although in this particular one, you could have fixed connections at the bottom. And reviewing a bit of statics here. Wonderful, perfect drawings we always make. Or I always make. Okay, so let's show the lateral loads on here. Now this is just a qualitative example, so we'll just label them P1 and P2. P1, P2. And P1 and P2. Now, the problem with this, or the essential problem, or the essential task, we might say, with each of these frames, is that we gotta find a way of getting this load down to the foundation. So where would these point loads come from? Well, fundamentally what this would represent is, this would be, say, okay, imagine where the cladding of a building meets its floor slab. So for example, where the cladding of a building meets its floor slab. So for example, you have, when I say cladding, I mean like either in a house, it could be something like siding or brick, or in a taller building, or it could also be the windows. If you have a large glass skyscraper, it would be the big window panels all the way along. Whatever the facing material of a building is, that load doesn't get carried all the way to the foundation, except if it's a very short building maybe, but it doesn't get carried all the way to the foundation via the actual paneling. The only thing that, say, the windows have to do is deliver. If there's a window right here, all it has to do, or if there's glass right here, I should say, all it has to do is to carry, the only load it has to carry is to deliver this load to the frame here, and the frame here, the floor slab here, and the floor slab here. But anyway, we still need to be able to resist this load. So if these are, if you think about this, imagine if I were to create imagine if all of these are pin connections. And in braced frames, they essentially are. Or sorry, in braced frames, they essentially are. So imagine if I had pin connections for each of these. Imagine if I had pin, 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 and then also at the foundation, pin connections. So if you've ever played with if you imagine, now these of course are structural elements, they're not literally going to have pins, but if you want to get a sense of this, imagine making a frame with, I don't know, something like, take some sticks, just simple wooden sticks, and connect them together with tape. create a little cube and imagine pushing against it on its side, and you can see how pin connections, if everything in a frame is a pin connection, they're really not capable of resisting any kind of lateral load. What this thing's going to want to do is it's just going to want to flop over. It's going to want to, if you have it, maybe I can draw this a bit over here. If one of the bays was originally like this, when you apply a load to it, it's just going to flop on over like this. And that's not going to do any good in terms of keeping your structure up. The pin connections themselves will do nothing to resist the lateral load. They can definitely transfer vertical load, but if your entire frame is connected with pin connections, and again, the definition of pin connection is one that can only transfer shear and not moment, then you're under any lateral load, your frame is just going to flop on over. So how do we deal with this in a braced frame? Well, it's in the name. We add braces. So braces are just some sort of element, a diagonal element that we add to a frame to reinforce it or to carry the lateral loads. So you still don't have any fixed connections. You can do all of this with pin connections. But the whole idea is that by adding diagonal braces to this, in order for this frame to flop on over like this, it's going to actually have to put one of these members into tension or compression. See, the problem with this, the reason that this is so weak, is that this frame can bend, or this frame can lean over without actually deforming any of the members. None of these members have to go into substantial compression or tension in order to tip it over. They can just change their rotations. But the moment you add bracing to a pin frame like this, if this thing wants to flop over, it cannot without putting one of these members into either tension or compression. So that is what allows you to use pin connections for everything. If you're going to do that, though, you have to add braces. So this does make things, and the thing about these braces, they don't have to be very heavy members. You can usually get by with very light members, something like depending on the building, you might be able to get away with something like an angle iron, or on very small buildings, you might even have things like it's not uncommon to actually see literally just steel cables serving as the braces. Now, if you're using angle irons, you can get by with just one brace. But if you're using cables, you'll need two braces in one bay because, obviously you can't push a rope. So if you have two cables, if you try to go this way, if you try to make it flop over this way to the right, this cable will go into tension while this one will just go slack. And if you try to pull it this way, this one's going to go into tension while this one won't be carrying any load. But anyway, however, also we need to keep in mind some terminology here. And realize that we don't have to actually brace every single one of the bays in a structure. So we could have, it probably wouldn't actually have it like this. If I'm going to show another bay, I could show that there's another bay here, and I could point out that not every one of the bays in a structure actually has to be braced to provide bracing to the entire frame. You can actually just brace maybe the middle one, or every third frame, or etc. You don't have to brace every single bay. Now, obviously, that would be the strongest option, but you don't have to do that. And in terms of the angles here, in terms of what's an ideal angle, the most efficient angle would actually be at a 45-degree angle. That's no surprise. But depending on the geometry of the bays, and again, terminology, we refer to one of these rectangles in a frame as a bay, if you don't remember that from structural analysis. But just some terminology. But we would call this a braced section, and this a leaner and a leaner. And a leaner. So this is carrying the lateral load, and these are just sort of being held up aloft by this one. So what are some benefits and drawbacks of this? Let's see this. So one of the benefits of it is that you're able to get away with simple pin connections. And when we get to connection design, we'll see that pin connections are much easier to both design and to manufacture. Or I should probably say fabricate rather than manufacture. Well, you can get away with just, for steel, you can get away with just a simple shear tab or something, but for a moment connection, you're going to need something that has much more involved flange plates, etc. And again, as a reminder, you have lateral resistance provided by the extension or contraction of, or the expansion or contraction of the brace. Provided by compression or tension of brace. Slash tension of the brace. Okay, so what if we don't want braces? Well, we can also talk about what is the downside of this. Well, the downside of this should be fairly obvious. Well, maybe not. Especially if you have a building. Now, if you have a building that the frame is just you have a simple building, the frame's just along the outside. Having braces along the outside, well, if it was something like a metal building like a workshop or a machine shed or something like that, that wouldn't be a problem. But if you have an office building or something, yes, you can add braces to it, even to exterior bays and such. But the problem with this is that this takes up a lot of space. So imagine, now architects are pretty good at hiding columns. You can usually embed those in walls. But braces, you really can't hide those very well. There are ways to do it, but they're all problematic. So like, imagine you have your hallway, and imagine you have a series of frames, and you're trying to make a hallway go through here. It's going to be very difficult in order to have an X-brace like this if you're trying to send a hallway through there. It's going to be very difficult architecturally. So the downside of braces is that they require space. Yes, they're very efficient and they allow for very simple connections, but the downside is they take up a lot of space in a building. Or if you have one of these on one of the exterior frames in a building, somewhere along a window, well, now you have a great big brace along your window blocking the view. And if you're an owner of an office building or something and you're trying to rent the space out, well, if you have a building that has a bunch of braces all over the windows, you're probably not going to be able to rent that out for quite as much as you would a building that just has clear windows, for example. But like everything, it's pluses and minuses, benefits, drawbacks, etc. So let's talk about the unbraced frame, or also known as the moment frame. So let's say our client says, I don't want any of that. I don't want any braces blocking the view. I don't want any braces blocking the hallways. I want to have a nice open floor. I want to have nice open floor plans. I don't want to have any braces in my building. So what do? Well, let's see. Let's finish drawing the soil or the foundation here, showing that we are transferring the load to the ground. Well, the only other option is that we have to stiffen up the connections. And so what we're going to do is we are going to make the connections. Now I'll draw them as all the connections, but it doesn't have to be. You can use just some of the connections as moment connections, and in most buildings that's what you actually do. Just like you don't need to add braces to every single frame or every single bay, you can usually get by with just some of the frames, or some of the connections, I should say, moment connections. And when I say moment connections, that means they are going to be they're going to be able to transfer moment. So these connections are going to resist rotation. So, what I mean when I say resist rotation, I don't mean that they're going to resist rotation. They're going to resist relative rotation. So, if I have an arrangement like this before load is applied, after load is applied, they're going to, maybe exaggerated of course, they're going to look something like this. So I had previously had columns coming in here and beams coming in here. After force is applied, they're going to look something like this. This kind of thing. Well, maybe not quite like that, more like, but everything still ends up entering and leaving that intersection at a right angle. I know that's not the best drawing there. Kind of hard to draw on the tablet here. Okay, but that's the basic idea. So you're there basically by having a fixed connection, or a rigid connection. These have different names. You can refer to them as fixed connections, rigid connections, moment connections, fixed frames, moment frames, unbraced frames, all the same thing. Again, here you're going to, for unbraced frames, you're going to need rigid, rigid or moment connections. Moment connections. And the lateral resistance is going to be provided by bending. Now, how does that make sense? Remember how I said that the angles are going to, the angles at all of these, relative to each other anyway, that they enter and leave the intersection, is going to be maintained at right angles, assuming they were initially at right angles in the unloaded case. Well, if I'm going to rotate them like this, I must end up putting all of these beams into some form of bending. If I'm going to twist this like this beam here is going to, look here, this beam is in negative bending, or sorry, this beam is in positive bending, this beam is in negative bending, and the column is also in bending. So basically I am forcing the energy of the lateral load to go somewhere, and the energy is going to go in to bending steel, or bending concrete. It's going to go into bending the beams and the columns. So really the connections themselves don't provide the lateral load resistance. The connections instead force the beams and columns into bending, and that is what provides your lateral resistance. Okay, so that is that's basically your two types of frames, either braced or unbraced frames, or braced or moment frames are sometimes also called. So next, let's look more at braced frames. There are several types of bracing that we might consider. So let me draw out a series of the various types of bracings. So let's next look at types of bracing. Types of bracing. And for each of these, I have 5 types of bracing I wish to discuss. And for each of these, I'm just going to draw a simple 2-bay structure, 1-story 2-bay structure. And I'll go ahead and put these with pin joints. And we'll say that, now I'm not going to show lateral load on these, but I will draw the system that is used to resist lateral load. But first I just want to draw out a few braces here, or a few frames here. Again, with pin joints all the way around. And I'll need 5 of these. And these are some you should be aware of. And each, again, has their own benefits and drawbacks, like everything else. And one more to go. And we'll label these, draw them, and then discuss them. Well, kind of all together. I could show the soil on each of these as well. Just to be clear that our structure is not floating through or flying through the air. We tend not to like it when our structures fly through the air. Normally that requires a tornado, and that's usually a bad day. So we won't worry about that. We're gonna draw trees, happy trees. Well, I can't quite draw that, but many's in the way. We'll just say there's soil there too. Okay, so let me label each of these first, and then we'll discuss what they are. So the 5 types we need to be aware of, for now anyway, are cross bracing, K-brace, the K-brace or K-bracing, the knee brace, the 2-way brace. I'm just trying to give you some exposure to various terminology from they see in steel structures, and also shear wall. Well, that's not really, I don't necessarily consider that a type of brace, but it does occur, or it is a similar system that can resist lateral loading, and it's similar to braces in the sense that it is another structural element that is resisting lateral load, and we'll talk about this. Okay, so first of all, let's look at the cross bracing, also sometimes known as the X-brace. And it really is the most efficient one. This is what I drew previously, and it's just a nice X shape that comes across. You'll have 2 different members. You could get by with 2 angle irons, just some light structural member that only has to carry some tension. No, we don't have to worry about buckling because it's just in tension. And you have a set of them, so if one, you have a set of them so that if one goes into, so if one goes in, so in other words, if you have a load in one direction, one of them can go into tension. If load is coming from the other direction, then the other one can go into tension, and neither of them ever has to carry compressive loading. And so you can get away with long, slender members, and if you remember from mechanics and materials, long, slender members are terrible for compression because they have a tendency to buckle, but they're great, very efficient for tension. They have no problem with tension. All that matters in tension, of course, is, well, besides from connections, all that matters in tension is your cross-sectional area, and other things as well, but mainly that. So again, and also by using the cross brace like this, you can get away with using, you can have your angle as close to 45 degrees as possible, which, as we discussed, is the most efficient shape. Now, the downside of this, of course, is that this also, even though this is the most efficient one, see, nature is not kind, even though this is the most efficient shape, it is also the one that takes up the most space. You're going to have to give an entire frame to these things, and you're really not going to be able to put any kind of hallway, any window, or anything there. It's just going to take up a whole lot of space. So it's the most efficient. If you've got space for it, it's great, but it comes at a heavy price. K-brace still takes up a lot of space, but gives you a little more room. It's going to be something like this. So you have a K coming in at 2 in one direction. Now I've seen you can have K-braces like this, or you could have the K-braces like this if they're across 2 floors or something. But the K-brace basically at one point it's going to meet at the middle of a frame, and then in one dimension it's going to meet at the middle of the frame, and the other it's going to meet at the ends of the frames. So something like this. Now the advantage of this is that if you can probably just imagine putting a hallway through there. So what I always come back to if you're thinking about buildings. So if you did this right, or if you could do this right, you might actually have enough room to just put a hallway through there, so you could use the space without actually interfering much with the operation of your building. But still, that would be a bit problematic. It's not quite as efficient as the cross bracing, but it's still fairly efficient. Now, next we have the knee brace, and this one is this is really providing, really trading off efficiency for function. So here, or for architectural function. So here, we're not crossing the entire frame in either direction. We have something going from a midpoint to a midpoint and a midpoint to a midpoint. This is the least efficient one of all of these structurally. So you might end up needing more of these. Maybe the members need to be larger, whatever. But the advantage is this doesn't take up that much space. So this one, if you're really constrained for architectural space, or you got an architect breathing down your neck, this one might be what you have to use. I'll come back to shear walls in a bit. And a two-way brace is really just a same principle as the cross bracing, except so you get the same efficiency. Although I suppose you could design a two-way brace like that, but maybe that's not seen very much. But just depending. But of course, these come in. I'm just giving you some generic families. These come in innumerable variants. But the two-way brace, it's called a two-way brace. It's called a two-way brace because the brace will be capable of carrying both compression and tension. So unlike in all the others anyway, all of the others, when you have lateral load applied in one direction, one member will carry the load and tension. When you have load applied in the other direction, the other member will carry the load and tension. In the two-way brace, however, the same member does double duty. So that means with this that you can't get away with using a very light member. You have to use something that has a substantial buckling resistance. So you're not going to be using something like an angle iron. You definitely can't use something like a cable like you can on some light one-way braces. But you might need to use something like a pipe or maybe a small wide flange shape or something like that. But your shape becomes more limited because you actually now also have to resist compressive load, which means you have to be able to resist buckling. Okay, so moving on. Or not moving on yet. There's one final thing we need to discuss, and that's the shear wall. Well, the shear wall is very literally just a big, heavy wall. Just a big old wall that you usually made out of concrete, sometimes masonry, sometimes heavily steel reinforced, just depending on how you're building it. maybe in very rare cases out of heavy steel plate. I don't know if I've ever seen that before, but I'm sure someone's done it at some point. But basically, it's just a heavy concrete or masonry wall, usually concrete in a lot of buildings. And the way this works is, well, imagine if you just have a very heavy concrete wall. If I just have a very heavy wall, if I want to cause this thing to collapse to the right, like I drew previously on the last slide, I'm just going to basically have to shear this thing in half. I'm going to have to fracture this wall before I can get this frame to bend over. So it's called a shear wall because of that. I put basically the wall itself, especially on a taller building, acts like an enormous beam. And if I want to cause the entire building to bend over or flop over or overturn, you might say, I have to apply enough shear to actually just shear right through that shear wall. And this tends to be used quite a bit, especially in taller buildings. And one area it's used quite a bit, especially an area that I see it a lot, is if you look at buildings that are, say, 3-4 story steel frame buildings, especially 5-6, that up to that height. You see it a lot in like office buildings, maybe doctors' office buildings, that kind of thing. Just watch that kind of mid-rise steel construction as it goes up. Well, if you remember things about your building codes, well, of course you need for taller buildings, or really any size building that has a lot of people in it, any building beyond a certain size, anything really more elaborate than a small apartment building or something, you need emergency stairwells. And so you need for any kind of large building, you're going to need heavily reinforced stairwells. You need stairwells that can withstand a very hot, very long burning fire in order so that people can evacuate the building in case of fire. Well, if you're already, and so the easiest way to do that is to make it out of concrete. Now, there are other materials you can use, but concrete is obviously very fire resistant. And if you're building a big steel building, and you're already having to construct this great big concrete core for fire resistance, you might as well make it carry some shear as well. You know, you'd be foolish to, have this great big concrete core in the middle of your building for fire purposes, but then not count it to carry any load and just use, say, fixed connections for everything to carry all your shear load. And that wouldn't be very efficient. You could do that if you want and had all the money in the world, but nobody's really going to do that. So in cases like that, though, that also illustrates that this is not I've labeled these kind of very much an either-or option. In reality, in real structures and real buildings, it's not either or. You have many different options, and in fact, in a big steel building like that, you might have all of the above. You might have shear walls, you might have braces, you might have some moment connections in there. It really depends on the architecture, essentially. So, in some areas of the building where, you're going to have that, if a particular frame in a building is going to be embedded in a wall anyway, go ahead and put a brace there. Why not? Save on the complicated connection. So that'll carry some of your shear in that part of the building. If you have a space that you really need to open views and you can't have any braces, use moment connections in that part of the building. If you have a big shear wall, if you have a big concrete frame or a big concrete wall or a big concrete box in the middle of your building to carry your stairwell or your stairwells and your elevator shafts as well, might as well make that a shear wall, make it bigger, make it strong enough to serve as that, and then just have that carry a lot of the shear for that area of the building and the rest of the building as well. So when I introduce these things here, I'm drawing them as and explaining them as if your building has to have just one of these things and you have to go all in on one of these strategies for carrying lateral load. But in reality, it's in most real structures you have a combination of these things. Again, because structural engineering, your building or your structure has to be able to satisfy many purposes. That you can't just have a free hand and design to your heart's content, and you can't just go with what's absolutely the most efficient. And that doesn't even necessarily come from architecture. You can have the same thing in industrial buildings. So, for example, like an oil platform or something. Sometimes you can get away with using braces. Sometimes you can't. If you have an area of the platform, the offshore platform, that has a lot of equipment, and you need to put a lot of pig launchers or something in there, or you need a gantry that moves around, or a equipment lifting mechanism that needs to move around, and a brace would get in the way. Well, you can't put a brace there, so maybe you have to use moment connections there. It all comes down to the type of structure you have, what its purpose is going to be, etc. So next, I would like to look at some diaphragm action. All right, I'd like to look at diaphragm action. So let's see what we mean by that. That's the last sort of lateral load distribution topic that I want to look at. So we haven't really discussed yet how the lateral load finds its way to the columns. We've said that the braces will resist the lateral load in the case of a brace frame or a shear wall will, but how does the lateral load actually get to the columns? So let's look at now previously I drew these frames as little stick frames, or I drew these beams as little sticks. But in reality, we know that buildings don't tend to have those, at least big commercial and industrial buildings. What you tend to have at those floors is big old concrete slabs. 4 inches thick, 5 inches thick, 6, 7, 8, or more, depending how what kind of load and spans you have. But anyway, so let me draw a frame here, and let me draw each of these stories. I'm going to draw a 2-story building. So this would be like a 2-story building with a roof slab above it. Something like this. And I'll put some little hashing in there just to make clear we're talking about a solid, big old slab of concrete. Same thing up here. And then maybe we can show some pin connections here. And leading to the dirt. Okay. Then I'll show the load that's applied to this. So let's say we have some wind load on this thing, applying a big lateral load here. Big lateral load here, some sort of distributed load W. Okay, so as I mentioned previously, the cladding is going to distribute the distributed lateral load, or so the most of your lateral loads, like wind, they're applied not at a point, but as over an area, Like wind, it's a pressure force. So the first structural or the first element, not necessarily, I don't know if you'd call it a structural element. I suppose you could in certain contexts. The first element of the building that's going to experience this lateral load is going to be the veneer or the facade, the cladding, whether it's a brick, or whether it's vinyl siding, or whether it's wood, or whether it's glass, or whatever the outside of the walls of the building are made of at any given point. They're going to be the first thing that experiences lateral loading. And they're going to take, they can't, of course, the cladding is not designed to resist substantial lateral load itself. I mean, if you imagine the windows on a 10-story building. Imagine if you just removed all the structure behind them and just stacked the window panels up in a big tower by themselves and maybe welded them together or something. The slightest breeze that is going to knock that thing over. The window panels themselves do not resist load. They do resist it a slight amount. If you think about the lateral load right here, like a window actually acts like a very tiny beam. It ends up distributing it has to carry a little bit of bending moment, a teensy tiny bit of bending moment, as it distributes the load to the slab above and the slab below. But in terms of the overall global building performance, they don't really carry a substantial load. The cladding only really serves to distribute the load to the floor slab above and the floor slab below, or to the base here. Okay, so it ends up in the slab here. Then what happens to it? Well, ultimately, it's got to find its way to the dirt. It's got to find its way to the soil. So how does it get there? Well, it's got to get to the columns. How does it get to the columns? It gets there through the slab. And we call these things, and they don't necessarily have to be slabs. They could be a very strong structural frame, etc. But we call this thing a diaphragm, especially if you have a rigid diaphragm. Diaphragms distribute lateral loads to columns. Diaphragms distribute lateral load to columns. That is their function. well, also actually, hold up the live load and dead load and the people and everything else. But so it turns out that when you build a concrete floor, when you build a concrete slab, its main function is actually, or originally, is to carry to gather the vertical loads, your live load, your dead load, etc. But it usually is so good at that. Not so good at it. It needs to carry. It needs to be so thick in order to do that, that it also serves as a very good load distribution mechanism. So when the cladding delivers the load to these diaphragms here, this essentially is a big honking slab of concrete. It doesn't deform much. So instead, it ends up distributing the load equally between these columns, assuming it's a rigid diaphragm. There's also such thing as flexible diaphragms, but we're going to focus mainly on rigid diaphragms for simplicity here. So in other words, if I want to figure out how much load each of these columns gets in terms of lateral load, I could find, what the total, I would take half of this height here, half of this distributed load here, apply it to this diaphragm and say, oh, what each of these columns, assuming rigid diaphragm action, assuming it's going to be able to efficiently distribute load, each of these columns will end up carrying a third of the load. And so when we say distribute load, if you imagine we had a very flexible diaphragm or no diaphragm at all. If we didn't have something to distribute the load, this poor column here would have to carry all of this vertical load. It would not be able, all this lateral load. It would not be able to distribute it to the frame as a whole, so this column would need to be very beefy. But by having a very rigid diaphragm, you're able to distribute your load across your columns. And that's where you can start using things like braces, shear walls, etc. Without a rigid diaphragm or without some way to distribute your lateral loading, you can have the best braces in the world. I mean, I can have a great set of braces here and here, but if I don't have a nice rigid diaphragm to get that load to that brace, this poor column is going to have to take all of the loading. So it's just a diaphragm is a rigid system. Maybe actually I can provide a bit better written explanation. No, the battery's running low. That's not good. Probably should have plugged her in first. Okay, so let me break after this. A diaphragm is a rigid element. That's a lovely S. Typically a floor slab, as we mentioned. A floor slab that serves to distribute and gather lateral loads to resisting members. That serves to gather and distribute keep going to the next page. Lateral load to resisting members or elements. Members or elements. So members like beams and columns, elements like a shear wall. I usually don't consider a shear wall a member. I tend to think of that as an element. A member is a structural member is something that has a very clear longitudinal axis, something that really has some length to it. Resisting members or elements. All right, I think I'll take a quick break there, and so I can plug this computer in. All right, and we'll be back.